Hello and welcome to part 5 of Pumps in PEL. So just to recap where we're up to, we've been modelling a relatively simple little system. We've been looking at how we might size this pump. So we've worked out a system curve, we've looked at a pump curve, and that we found the duty point, and then we've checked the MPSH, and we looked at the power requirements to actually pump that fluid from tank A to tank B. So that's all been in Capri. What I want to do in this one is actually look at how we would do this in Flonet. So Flonet looks a little bit like this. So this is the program for doing incompressible flow. It will do networks, but we're just going to do a simple straight pipe at this point. And all we've got here is a representation, that little sketch that I've just shown you. So this is our inlet tank. Now, just to explain a little bit what's going on with that fitting, is that's actually two nodes bolted together in the background. And the reason why we did that is you might want to, around pumps, have a recirc line back in there if you want to ensure minimum flow. And previously you'd have two nodes to do that. It made more sense and more intuitive to have a single node. So then you can move about, make sure you got consistency with the pressures and temperatures, whatever it might be within that node. So that's why that looks like that and makes it a little bit easier for the users. So if I double click on our tank, so the height of the top inlet, that's that bit there, which we're not worried about. Height of the bottom outlet. So we need a datum point for all this. And if I go back to my little sketch, we said the datum was basically through the middle of the pump. It's 2 meters above that. So I've got 2 meters from the bottom outlet to my pump. I've got a meter's worth of liquid in there. And then I've got 15 degrees Celsius temperature. I've defined my fluid. So with the fluids, eventually when they click the physical properties, it's water at 15 degrees C. I'm not going to start doing that because we need to get through this 5 minute short, and there's other 5 minute shorts that will demonstrate that interface with FizzPack. What I really want to focus on this bit is here you can see this little table is produced 3 rows, 3 sets of properties. What Flonet does is it interpolates between points. It will, if it needs to, extrapolate as well, and you don't really want it extrapolating. So when you're setting these up and think about in your ranges of temperatures and pressures, just make sure that you know what you're going to do is compassed within that range you've defined. So for our system, we're going from atmospheric pressure. There's not a huge amount of pressure on, so I've done 0 to 10. That will cover everything we're doing on the pressure side. I've assumed the flow is 15 degrees C, so I've done 5 to 25 and a 15 in there. So I've definitely covered the conditions I'm going to be doing, and the physical properties will be interpolated, not sort of going out beyond the bounds of what we know. And if you want more points, you can change that. It defaults to 3. You can have 4, 5, 6, however many you wanted. So that's what we've done with the fluid. And you can see there our temperature is 15 degrees C. So that's set up our initial tank. The pipe is relatively simple, 3 meters, shed 40, mild steel, slightly corroded. We said a K is 3, just for example, as we go through this, and let's estimate the mass flow. Don't worry too much about that at the moment. So that's all good and fine. Again, you've got the little ellipses here if you want to press these to open up the little tools to get the pipe diameter, the roughness, your K value calculator, etc. We've done the same on the discharge pipe. So 10 meters, same pipe diameter in this particular example, roughness 15 on our K value. Nothing exciting there. Our discharge node, so although that's shown as a straight pipe, this is where I've put the height difference in. So from my discharge, I've said it's all the way, it's 5 meters above my datum line. So I've put that 5 meters in there. That's where it's picked it up. And then 15 degrees C again, just the temperature. We need the model to calculate something. We need to fix something. We know, or we're assuming the pressure in that discharge tank is atmospheric. So I've said that's 0 bar gauge, and I'm fixing that. So then it will start to work out the flow rates to make sure we've got that 0 bar gauge at that point. So that just leaves our little pump left to do. So if I look at my little pump, so there's a few things just to be a little bit careful of when we're specifying this pump. A couple of ways we could do this. We could do a define delta P for your pump, just do it as off a basically a simple point. I much rather put a curve in, so I've selected curve. And if I go to curve here, it's a little bit of a funny graph at the minute. We'll have a look at that in a moment. So looking at the graph reader, we'll move that across. Let's clear all those points. So what's really important with this one, and actually we'll redo that graph, is we'll reset the extents, origin, and discharge. But before we start clicking points, 125 at the top there, 0, 0, 400. But we need the units now. We need to make sure the units are right. So feet and US gallons per minute, because when we go back into the table, my model is set up around meters and meters cubed an hour. So if I get those units right, it'll do the conversion for me without me having to worry at all. So I'm going to click some points. Now you can see it's drawing the red line the best fit. For this particular case, we can entirely ignore that. So we'll turn that off for a minute. That's if you're going to start using the data in Excel. So we'll just remove that. But we got some points. Do a few more, try and make it not look quite so wobbly as last time. Press OK. And then that's my little wobble in the middle. But he's put a pump curve in. So that's not too bad. Probably spend a bit more time getting that a little bit smoother. But for the purpose of this, it's there or thereabouts. You can put the speed in and the impeller diameter. So what's the curve based on? And then if you want to change your pump speed, you've got VSDs, you want to change the installed diameter, then Flonet will make some approximations and change the flows depending on what you change those to. So we've got a pump, got a pump curve. Other things, just quickly, just little gotchas that we've got to be careful of. Upstream, just check that, no, that's our tank, that's good, it's going down to the exit. We haven't got a temperature rise across our pump. Pump height inlet. If you remember our diagram, we've got 2 meters difference between here and here. So if you click inlet conditions, what the model will automatically do by default is that will be unticked, and it will assume the pump is at the same height as the bottom of this tank, which we don't want. So I've had to override that condition, and I want that at 0 meters. So that gets my height correct, that drop down. And similarly, you could check the discharge side. What that's going to do is going to pick up and assume it's at the same height of the pump. Some people like to get, into the detail, and actually, your discharge of your pump is slightly higher than your inlet, so you could add that in here if you wanted to. For the purpose of exercise, that's not really important for me. But again, same sort of thing. You can override it and put in that height difference across the pump if you so choose. So now we've got our pump. Press OK. We're going to press calculate. Click our results. And the first thing we'll look at is our pump. So we can see if I'd highlight it here, it's showing our pump. It's giving us our inlet and outlet. And it's giving us a flow rate. And we've got a 12 meter head and 22 and a bit meters cubed an hour. If I go back to my original system curve, I'm not a million miles away. 23 meters cubed an hour, 22.6, 12 meters. I'm at 12 meters. So I'm in the same place. And we saw that pump curve was a little bit wobbly. I wasn't particularly good at clicking on it while talking. But fundamentally, we're in exactly the same place, which is nice. So what we did at Capri is matching what we did in Flonet if you have some accuracy with a mouse. Other things we want to look at in this particular one, we can look at the pipes. So again, we can see that the flow rates, the velocities, the differentials through that inlet and through a discharge side. We can look at the conditions in the nodes as well. And you can see which one's a sink, which one's a source. So all the information we need to check the elevations, quite important what we're doing. There's our pump at 0. So if you hadn't done that pump at 0, that's where you would pick up. So it's worth checking your nose to make sure you got the height changes. So there we go. That's how we would do it from Excel into Flonet. Hope that makes sense. Thank you very much.